Hi-ho everyone, my name is Max Joyce here, Physics 2211, lab number 4, oscillation. Alright, quick overview, we're doing an introduction, we're going to talk about some springs, we're going to look at a tracker model, we're going to look at a computational model, and then we're going to draw some conclusions. Introduction, Newton's second law, springs and energy, equations are as shown. We're going to go into those three topics in a little bit of depth. Alright, so talking about Newton's second law relates to net force or interactions to a change of momentum over some time period. That's what that first equation shows on the right there. And then we discover that final velocity is dependent on the net force and the amount of time the net force is acting on the system. That's essentially what we get from that bottom equation right there. Alright, those are going to come into play when we do a little bit of our coding. Alright, so springs. Springs oscillate, so the net force will not always necessarily be constant, alright? So for this example, our springs are going to have a tons of force values depending on where it's at in its oscillation range, essentially. So that's what that delta x really means. So I'm going to skip to that. What is k and x? So of course, k is just the spring constant. It's a value dependent or independent of the length, I guess. It's dependent of the type of spring you're using. And then that delta x is just your change in length, essentially. So you're going to have your original length, which is normally denoted as L naught, and then the length of the spring when it was compressed, that's usually denoted as L. So you have L minus L naught, and that's kind of how you see how much your spring has changed in its length. All right, which in this lab we're going to call S. All right, so talking about energy. As you can see, that's like the energy graph from this lab, which you'll see later as well. But systems versus surroundings, yeah, everything's in our system, so our surroundings is nothing. So that's why the change in energy is 0, because there's nothing in our surroundings applying a net force to our system, which is the spring and the earth. Yeah, two types of energy, potential and kinetic. Potential energy can be spring, gravitational, electric. Kinetic energy can be translational and rotational. All right, so spring video. We all saw this, goes up, goes down, goes up, goes down. All right, that's enough. Tracker model, same video as before, and just did the tracker with it. Revolutionary stuff here. We got those graphs, which will come into play in just a moment, or just later, I guess. All right, so moving on to the actual cool stuff, the coding bit. So what you see now are your initial conditions. The ball's mass was the mass of the thing that's oscillating was given to us in one of the pre-lecture videos. I just took that, and then the initial position vector I got from the graph in the table that we're given. Of course, G is 9.8. The K sub S is just the spring constant, and we were given that also in one of the pre-lecture videos, so I just took that. Same thing with L naught, 0.123. And then we know that L is just going to be, like I said earlier, the ball position minus the spring position. And then that's going to be the length of like the spring itself, essentially. And then L hat's going to be, of course, that's just how you find a unit vector. And then S is just going to be the magnitude of L minus L hat, or excuse me, L naught. All right, and then going on to the energies, which is below. These are just like standard equations that we learned in class. So we know kinetic K equals 1/2 mv squared, UG equals mg delta y, US equals 1/2 kx squared, or in this s squared, and then of course all of our total energy is going to be kinetic plus gravitational plus our spring energy. All right, so this was actually our time loop right here. Really, you just had to calculate for like the force of gravity and the force of the spring, which we showed the equation before. Pretty standard stuff there. I will say that we had to use the velocity update formula and position update formula a little bit lower when we're applying Newton's second law. And once again, this is just kind of letting us update the everything. Really update the K UG, US, the total energy, all while this is going on in this time loop. All right, so this is essentially the results. I showed the energy graph before, but this is like what we want to see. So we know that the spring potential energy is going to be the lowest when kinetic energy is the highest. And the same thing for like gravitational energy, of course. And we can see that everything is constant. And we can also see that K is equal to 0 when the potential energy of the spring is at its most, because it's at rest when it's being pulled the most. That's just a property of oscillating stuff. And then the graphs on the right, of course, you can see they pretty much line up pretty good on myself for the tracker. All right, so talking about these questions real quick, we already talked about why the energy principle is satisfied, because we included everything in our system. And then talking about the estimates of oscillations period. Yeah, so they're kind of the same period, of course, because it's the same spring. Now, actually, excuse me, they're not kind of the same period because they're moving at different speeds, because it's just being, there's different forces acting on it, of course, so your period's going to be a little bit different in the X and Y position. But of course, it's the time stays the same. All right, thanks.